Ever wondered how airlines keep planes moving efficiently between flights? It's all about turnaround time, the critical window when passengers disembark, planes get cleaned, refueled, and prepped for the next journey. But predicting how long this process will take isn't simple. While external factors like weather or delays play a role, the core processes follow patterns tied to the plane type, airport setup, and scheduled timing. So how do experts predict these turnaround times? They use machine learning models, like DecisionTree, Random Forest, and XGBoost, trained on historical data. But here's the catch. Real-world data is often limited or proprietary. That's where synthetic data comes in, computer-generated data that mimics real patterns. But not all synthetic data is created equal. In our study, we tested 4 synthetic data generators, GaussianCopula, CTGAN, TabSyn, and REaLTabFormer, against real data. The results? REaLTabFormer and TabSyn blew the others out of the water. They achieved nearly 97% of the predictive power of real data, while simpler tools like GaussianCopula lagged far behind. Let's break down the numbers. For metrics like RMSE, which measures prediction error, REaLTabFormer's errors were just 3% higher than real data. That's incredible. Meanwhile, models trained on CTGAN data showed more significant gaps. But why does this matter? It's not just about accuracy, it's about understanding the right factors. Our analysis showed that scheduled time, airport specifics, and flight details were the top predictors of turnaround time. And here's the kicker. REaLTabFormer and TabSyn preserved these critical relationships perfectly. This means airlines can use their synthetic data to make informed decisions about crew scheduling, gate assignments, and resource planning, without needing access to sensitive real-world records. But there's a limit to what we can predict. Even with real data, the best models only explained about 44% of the variation in turnaround times. Why? Because aviation is inherently unpredictable. Weather, last-minute changes, and human factors all play a role. So while synthetic data is a game changer, it's important to build systems that account for uncertainty, like having backup plans or flexible schedules. So what's the takeaway? If you're an airline or a researcher, REaLTabFormer is your go-to tool for high-fidelity synthetic data. If you need faster results, TabSyn is a strong contender. But avoid GaussianCopula for complex tasks. It's better suited for simple analyses. This research shows that synthetic data isn't just a shortcut, it's a powerful enabler for innovation. By bridging the gap between limited real-world data and the need for advanced analytics, it's helping the aviation industry plan smarter, adapt faster, and keep planes flying. Now let's dive into the technical heart of these tools. How do TabSyn and REaLTabFormer create synthetic flight data that's almost indistinguishable from real-world records? Starting with TabSyn, imagine you have a giant jigsaw puzzle where each piece is a number or a category, like flight times or airline codes. The decoder in TabSyn is like a super smart puzzle solver. It takes scrambled pieces, called latent vectors, and rebuilds them into the original data. Here's the trick. It uses a transformer decoder, which is like a team of experts analyzing the puzzle. They look at each piece in context, not just alone, to figure out the best fit. Then a column detokenizer turns those puzzle pieces back into real data. Numbers stay numbers, and airline codes stay codes. But how does it learn to solve the puzzle in the first place? TabSyn's training has 2 phases. First, it uses a variational autoencoder, VAE, to compress data into a compact, latent space, like distilling a complex recipe into a few key ingredients. The VAE balances 2 goals: reconstructing the data accurately and keeping the latent space flexible. The adaptive KL divergence part. Think of it as a teacher adjusting the difficulty, starting strict, then letting the model explore more as it learns. Then comes the diffusion model, which adds creativity. It starts with random noise, like a blank canvas, and gradually adds details guided by the VAE's learned patterns. It's like teaching a robot to paint by first showing it thousands of examples, and then letting it experiment. After 1,000 rounds of refinement, it produces synthetic flight records that mirror real-world data, without ever copying it. Now let's switch gears to REaLTabFormer, which takes a different approach. Instead of compressing data, it treats each flight record as a sentence. Think of a flight's details, airline departure time, delays, as words in a story. REaLTabFormer uses a GPT-2-style transformer to generate these stories, 1 token at a time. But how does it handle numbers and categories? The data transformer first converts everything into tokens. Delays and durations become strings of characters, like 12.5 becomes 1, 2, 5, while airlines and airports get unique codes. This way, the model sees patterns in the data as if it were learning a language, recognizing that AA always comes before JFK, or that delays often follow specific time patterns. By the end, it's not just guessing. It's building coherent, realistic flight records that follow the same rules as real data. Both TabSyn and REaLTabFormer are game changers for privacy-preserving data science. They let researchers test ideas, train algorithms, and spot trends without touching sensitive information. Next time you hear about synthetic data, you'll know it's not just random numbers. It's AI solving a puzzle smarter than we ever could. So the next time you're at the airport, remember, behind the scenes, data scientists are working hard to turn complex processes into predictable patterns. And with tools like TabSyn and REaLTabFormer, the future of data-driven aviation is brighter and more precise than ever.